thank you for the possibility to talk here today. My name is Troels. I'm heading up our global quantum hub, KPMG's global quantum hub, and I'm here today with Astrid to talk about a project that we have done together that relates to route optimization. So this is about early initial findings on how to apply quantum-inspired optimization to solve route optimization problems. So we are starting out with an introduction to the problem. So Astrid will give an introduction to herself and talk about the business problem at hand that we've been solving together looking into solving using quantum. Then I will talk more about the quantum methods, how we formulate this as a quantum problem, what kind of methods we use, and then we finally talk about the business outcomes of the project. And we hope to leave some time for questions. Yes, Astrid, do you want to take over?
Yes, thank you, Troels. I'm Astrid, and I'm heading up the advanced analytics team in TDC Net. It's a small national network company, communications company in Denmark. This is me. But we recently communicated to the authorities that we had this really ambitious zero net carbon emission plan for 2030, which is why we got some nice pictures taken with our cars. So me and the sustainability manager, Peter, here we have really tried to find many possibilities for how we can actually reach that goal by 2030. And one of them is to look into our driving patterns, and our ambition there is to reduce that by 25%. That's why there's such a nice picture here. So the problem we are looking at, since we are rather small, we have 850 technician vehicles. They're not all driving every day, but that's our fleet. And we have approximately 80,000 kilometers driven every day, which is twice around the world. And then we have approximately 1,000 orders and faults that we drive to nationwide. So kind of small compared to other network communication companies. But this is also why it's a little bit interesting to explore new technologies, etc., to see if we can actually become more efficient in solving this problem. Because even though it is small, it's still quite complex because we have a lot of constraints. And those constraints, I list them here, is like we have the start and end location of all the technicians. They're not coming from the same start and end point. They're coming from typically their own addresses. We have 150 different kinds of skills, so the company is covering 4 different technologies, copper, coax, fiber, and mobile. So there's a lot of different skills there. And also there is the capacity planning, who is available to work and how many do we actually need. And then there is overtime, there is multi-faults. Multi-faults requires multiple technicians, or they require the technician to go multiple places, etc. It's very complex. There's the SLAs, so some of the customers, we need to fix their faults very fast. If it's a hospital, if it's the alarm systems, that's really urgent. And then others, there is a more loose SLA. Then we have equipment warehouse visits. If the technician hasn't got the right equipment to solve the issue, he needs to make a stop. So all of these constraints. And then there's of course the important lunchtime, which we also have to take into consideration. So all of these constraints, even the problem size, even though we are a small country, it's a quite complex problem. And we do have a workforce management software today, which has a classic routing optimization engine built in. However, the many changes that happens throughout the day is always difficult to let's say find a global optimal solution for as they happen. So changes as fault coming in, visits whenever the technician can take the lunch break or not, and also the job time, how much time it actually takes. We have predictions, however, stuff happens. Sometimes it's not as easy as it looks, etc. So, in my team, the Advanced Analytics team, we have tried to address, let's say, this routing problem, which today we solve using classic routing optimization, but rather inefficiently. We try to address this threefold. Number one, my team is using AI and machine learning and also classic operations research methods to try to be better at long-term planning, but also forecasting the actual day, events of the actual day. So how many faults, etc. And we're using lots of various data sources for doing so, but typically machine learning and those kind of methods on a classic computer. However, we also wanted to increase the fraction of automatic dispatch, which is today around 30%, and we want to reach, at least 90%, which is, of course, a little bit ambitious in this area because there is all these changes. So our hope is that we can use quantum technology to create these scenarios where we can model various process changes, various changes to the actual, let's say, overall long-term planning and see the efficiency. So actually doing that on a faster time scale than we can today for testing and optimizing the potential of the reduction in driving. And then there is also the intraday potential, so the speed, hopefully, of quantum technology can be supporting us in actually getting better solutions when there are changes during the day. So the two latter is where we've partnered up with KPMG to actually explore the quantum inspired optimization on this problem to see if there is actually an upside. And we are looking into the scenario builder, so basically testing assumptions, sort of in the back office away from operations, where we would use quantum optimization to test out various fairly complex composition in terms of what is the optimal skills, broadness of the technician, what is the optimal technician position, and what is the optimal number of technicians, for instance, to solve a period of time of already, either orders and forecasted faults coming in. And then there is also the intraday sort of faster optimizations whenever there is a change. So those two are the areas that we've been testing together with KPMG, and now Troels is going to explain a little bit more in detail.
Thank you so much, Astrid. So, as Astrid mentioned, we've been using quantum inspired to test out how we can solve these problems. And I'm just going to take this one very quickly because I think all of you are aware of the approaches to do quantum, to focus on either gate-based or quantum annealing or quantum inspired. And in this case, we are using QUBO formulations, which have the nice property that they can run on all three hardwares. Sorry, all three hardwares. And in this case, we are running it on classical hardware. So we are out on the right-hand side where we are running it on classical hardware, digital annealers, these kind of things. And the benefits that we're seeing is faster time to solution. Astrid also talked about using it for the intraday. It's really a requirement to have fast time to solution if you want to update it when a technician arrives and a client isn't home or a technician gets sick or all of the kind of things that happen during the day, and you can't wait 2 hours for the solution to find some new plan. So you need it in minutes. and also find solutions of better quality. We'll come back to the actual outcome of this one, but this was one of our initial KPIs to also reduce the mileage, as Astrid started out, saying that it's TDC's ambition to become carbon neutral. So of course the kilometer you're not driving is clearly a kilometer where you're not leaving a carbon footprint. And one of the reasons that we're able to do that is that we're able to attack larger and more complex problems. We see this across industries that often today, a lot of approximations are done before the problem is being solved, simply because it would take too long to solve the full complexity. So that's also where we're getting a lot of the improvements in the quality, that we can simply attack the problems closer to their source. Finally, it's also quite a flexible setup here. We also saw that during the project, where we could, you can say, as we went on, as they talked about all the many constraints that there are in the problem, and it was actually possible to add these constraints as we were going along. It's not a new, completely new problem formulation when you add new constraints. It just adds it in an additive way, since we have the Q2B formulation. We saw financial companies being very early adopters of this technology. Those of you who were here for the previous talk also heard about applications of Q2B to portfolio optimization. And the financial industry was fast, but I think we can safely say, after also working with it in logistics and together with Astrid, that logistics looks to be an even better place for realizing much larger benefits than we saw here. So a little bit details on what we ended up doing. We tried a few different methods or a few different formulations. I'm not going to present all the methods that didn't provide good results. I'm going to present the method that provide good results, just to be efficient with your time as well. So the most efficient way we found this was to create a Q2B formulation of the assignment problem. So basically the problem of saying, which tasks should this technician solve during the day? Because Q2B is unconstrained by nature, so it was a little bit tricky to have Q2B, you can say, solve the entire problem, because then if it ends up missing some of the constraints somewhere, then it doesn't become a practical solution you can use in a given day. You can't just tell the technician to magically jump to the next location, because it violated our constraint. So we try to use the strength of Q2B, that it can really attack a very large problem and find good heuristics in a short amount of time. And we use that, recapping, we use that to do the assignment problem. So once the Q2B has run, we know which technician is supposed to visit which customers or which locations, and then we use more classical operations research in order to plan the actual route for each technician. Because by this time, it has been broken down into such small problems that it's extremely fast to run for each technician in order to find. So we use Q2B in order to really cut the problem up into easy chunks to solve, and then we use the strength of operations research in order to actually do the final routes. Yes, but let's look at the outcome, and maybe you guys can start preparing some questions, because we are leaving quite some time for questions. So here are the 3 KPIs that we were looking into. Primarily, there was the number of technicians that are needed on a given day, was the mileage that they drive, and then finally it was the runtime of the solution. And on technicians, the solutions we can find using quantum inspired resulted in using 17% less technicians on any given day. And when it comes to mileage, there we have a larger improvement, and I think we can say we were impressed that we could hit numbers this high, but we were looking into a 58% reduction in kilometers. And the final one was the runtime, and this was even more dramatic. So we were able to go down from basically hours to minutes. Yes, that was what we brought along. We have time for some questions.
All right. Do I see some hands here?
Thank you very much for the talk. So I'm Michel Craig from Multiverse Computing. Can you elaborate on what you mean by quantum inspired? Because it's a multifaceted terminology in the quantum area. Can you give more detail?
Yeah, sure. So the quantum inspired is some call it digital annealing. Fujitsu are calling it digital annealing. So that's when you're using classical hardware. So let me just go back a couple of slides. So that's where we're using classical hardware in order to simulate what goes on a quantum annealer. So we're using the QUBO formulation that we know can run on these quantum devices, both can run on the gate-based quantum computers using quantum approximate optimization algorithm, and can of course run on the quantum annealers that were also for instance, the ones from D-Wave that we heard about in the previous talk as well. The quantum annealer has been specifically built. It can only solve one problem. It can solve QUBO problems. But then I think the interesting part was that it turned out that you can use classical algorithms in order to simulate what goes on a quantum annealer. So you can use simulated annealing, you can use other methods as well, Monte Carlo methods, population annealing, and a good amount of other methods. And it actually turns out that perhaps I wouldn't have guessed that if you had asked me 3 years ago, but it actually turns out that it's quite efficient to solve using classical hardware. So that's what we mean with quantum inspired. Oh, okay, maybe you had a, yeah.
Marco Ranchito Energies. What type of hardware? Is this a full HPC server room with kind of thousands of cores and hundreds of terabytes of RAM?
Right. This was running on Fujitsu's digital annealer. So this is a special purpose chip that they have built to solve QUBO problems. Yeah.
So first, thank you. Great talk by both of you. Very interesting. I have 2 questions. One is, what is the data, the KPIs that you've shown are very impressive, but what is the baseline? Meaning, you started from someone putting the technician dispatch in Excel, brute force, and this is the baseline, or did you use any other machine learning AI to create the baseline? And the second, can you also provide metrics of how much would it cost? Meaning, I guess it's quite expensive hardware. Let's say I'm going to Amazon to list that. Okay, what are the implications? What kind of data you can provide me in terms of cost?
Right. Maybe I could start with the last question, and can you cover the first question? Yeah, maybe we can recover the microphone while I'm answering the last question, because we were of course estimating the cost of this, and you can say even with the 850 technician scenario, we are actually on a positive business case around the 3rd of January if we look over a year. So basically the compute cost we're talking about, you can say a couple of days of the savings here. That covers 1 year of compute time on this. So literally we were mapping it out and thinking, okay, so if you've got 365 days, after the first 2 days, the compute costs have been paid. Yeah, Astrid?
Yeah, and the baseline was taken from an actual day using the workforce management tool that we have as an enterprise software that we have. So we used that as a baseline, basically. So there was no manipulation or anything to the data to fit here. So yeah, so it looks interesting. There is one caveat. All of the constraints are not implemented yet. So we are at a stage where it looks really good theoretically. Obviously, the 58% is we knew the day that has already passed, so we knew exactly what was happening. So obviously, we will not be able to get 58% savings in driving, but if we can get half of that, we're also happy.
Great. All right, everybody, let's thank Astrid and Troels.
There was one more question
Oh,
if we
one
have
more
time,
question?
but I don't know how we.
Quick
are doing
one,
on
quick
time.
question.
So very quickly then, Marcin Dukowski from Aramco. Was your problem a spin glass?
I didn't hear that.
Was your problem a spin glass?
All right. We ended up formulating as 01, not as the spin class, but we could have formulated as a spin class as well.
Glass, the G. Glass. Less glass, but glass. Yeah. Like, was it complicated enough to actually benefit from quantum effects? Or can you prove that a classical solver will perform as well as quantum?
All right, but we are using a classical solver to solve this.